Chemical bonding explains why atoms join together to form substances. Atoms bond to achieve a more stable, lower energy arrangement, often by obtaining a full outer electron shell. In this chapter, we'll explore ionic, covalent, and metallic bonding, along with how bonding influences the properties of materials. Most atoms are more stable when they have a full outer shell of electrons. To achieve this, atoms either lose, gain, or share electrons. These different methods give rise to the three main types of bonding that determine the structure and behavior of substances. Chemical bonding explains how atoms combine to form substances and why those substances have particular physical and chemical properties. The three main types of strong bonding: ionic, covalent, and metallic bonding. These bonding types are then linked to different structures, such as giant ionic lattices, simple molecular substances, giant covalent, macromolecular structures, and giant metallic lattices. Ionic bonding occurs when electrons are transferred from a metal atom to a non-metal atom. This forms positive and negative ions, which are held together by strong electrostatic attractions. These attractions act in all directions throughout the giant ionic lattice. Ionic bonding is defined as the electrostatic attraction between oppositely charged ions formed by the transfer of electrons. This type of bonding typically occurs between metals and nonmetals due to their large difference in electronegativity. Metals, found on the left-hand side of the periodic table, tend to lose electrons to form positive ions, cations, while nonmetals, on the right-hand side, gain electrons to form negative ions, anions. Ionic compounds have high melting and boiling points because a large amount of energy is needed to overcome the strong electrostatic forces between ions. They conduct electricity when molten or dissolved, as the ions are free to move and carry charge. Ionic compounds form giant ionic lattices, which are three-dimensional, regular arrangements of alternating positive and negative ions. Each ion is surrounded by ions of opposite charge, maximizing attraction and minimizing repulsion. Firstly, ionic compounds have high melting and boiling points because a large amount of energy is needed to overcome the strong electrostatic attractions between ions throughout the lattice. Covalent bonding occurs when atoms share pairs of electrons. This usually happens between nonmetals. The shared electrons are attracted to both nuclei, creating a strong bond that holds the atoms together. Covalent bonding occurs between nonmetal atoms and is defined as a shared pair of electrons between two atoms. In this type of bonding, atoms share electrons in order to achieve a full outer shell and a more stable electron configuration. A single bond involves one shared pair of electrons, as seen in H or Cl. A double bond involves two shared pairs, as in O, while a triple bond involves three shared pairs, as in N. As the number of shared electron pairs increases, bond length decreases and bond strength increases. A dative covalent bond, also called a coordinate covalent bond, is a special type of chemical link where one atom provides both electrons for a shared pair. A dative covalent bond, also known as a coordinate bond, is a type of covalent bond where both electrons in the shared pair are supplied by one atom. Dative bonds are treated as covalent bonds because once formed, they are identical in strength and behavior to other covalent bonds. Molecular shape is predicted using VSEPR, valence shell electron pair repulsion, theory, which states that electron pairs around a central atom repel each other and push as far apart as possible to minimize this repulsion. Electron pair repulsion theory, commonly referred to as VSEPR theory, is used to predict the shapes of molecules and ions. Electron pairs around a central atom repel each other and arrange themselves as far apart as possible to minimize repulsion. The strength of repulsion follows the order: lone pair, lone pair, lone pair, bonding pair, bonding pair, bonding pair. Electronegativity is a measure of an atom's ability to attract the bonding pair of electrons. The greater the difference in electronegativity between two atoms, the more polar the bond becomes. Electronegativity is defined as the ability of an atom to attract the bonding pair of electrons in a covalent bond and determines whether a bond is polar or nonpolar. When two atoms with different electronegativities form a covalent bond, the bonding electrons are drawn closer to the more electronegative atom, creating a partial negative charge and a partial positive charge, plus. This results in a polar bond. Intermolecular forces are attractions between molecules rather than within them. Although much weaker than covalent or ionic bonds, they play an important role in determining melting points, boiling points, and solubility. Intermolecular forces are weak attractions between molecules and are distinct from the strong covalent, ionic, and metallic bonds within substances. London dispersion forces, permanent dipole-dipole interactions, and hydrogen bonding. London dispersion forces arise from temporary induced dipoles and are present in all molecules. Their strength increases with the number of electrons. Permanent dipole interactions occur between polar molecules, where the positive end of one molecule is attracted to the negative end of another. Hydrogen bonding is a particularly strong form of dipole interaction that occurs when hydrogen is bonded to nitrogen, oxygen, or fluorine and interacts with a lone pair on a neighboring molecule. Hydrogen bonding explains the unusually high boiling point of water and the solubility of alcohols. Metallic bonding is the attraction between positive metal ions and a sea of delocalized electrons. These mobile electrons hold the lattice together and explain why metals are good conductors of heat and electricity. Metallic bonding is defined as the electrostatic attraction between a lattice of positive metal ions and a sea of delocalized electrons. In metals, outer shell electrons are delocalized and free to move throughout the structure, while the positive ions remain in fixed positions. Metals conduct electricity because the delocalized electrons can move and carry charge. They are malleable and ductile because layers of ions can slide over each other without breaking the metallic bond, as the attraction between ions and electrons remains. Metallic bonding strength depends on factors such as the charge on the metal ion, the number of delocalized electrons, and the size of the ion. Comparing structure types for the different bonding structure: giant ionic, giant metallic, giant covalent, and simple molecular. Giant ionic structures consist of oppositely charged ions in a lattice and have high melting points and conductivity when molten. Giant metallic structures consist of positive ions and delocalized electrons, leading to conductivity and malleability. Giant covalent structures, such as diamond and silicon dioxide, contain extensive networks of covalent bonds, resulting in very high melting points and hardness. Simple molecular substances consist of small molecules held together by intermolecular forces, giving low melting points and poor conductivity. Giant covalent structures contain an extensive network of covalent bonds. Because these bonds extend throughout the entire structure, substances such as diamond and silicon dioxide have extremely high melting points and are very hard. Giant covalent, or macromolecular, structures consist of atoms joined by a continuous network of covalent bonds. Diamond is a classic example, where each carbon atom forms 4 covalent bonds in a tetrahedral arrangement, making it extremely hard with a very high melting point. Graphite also consists of carbon atoms, but each carbon forms only 3 covalent bonds, creating layers of hexagonal rings. 1 electron per carbon is delocalized, allowing graphite to conduct electricity. Weak forces between layers mean graphite is soft and slippery. Silicon dioxide has a similar giant covalent structure, with each silicon atom bonded to 4 oxygen atoms. Chemical bonding parameters are fundamentally governed by periodic atomic properties, which directly influence molecular architecture and thermodynamic behavior. Data analysis is an important skill. A substance with a very high melting point and electrical conductivity as a solid is likely to have metallic bonding, whereas a low melting point and lack of conductivity suggest a simple molecular structure. Calculations may include deducing empirical formulae of ionic compounds from ion charges. The shape of a molecule depends on the number of bonding pairs and lone pairs around the central atom. Electron pairs repel each other and arrange themselves to minimize repulsion, giving predictable molecular shapes. Exam questions often integrate several bonding concepts into one scenario. Using the VSEPR theory is used to identify the shape of ammonia, NH, with 3 bonding pairs and 1 lone pair around nitrogen, giving a trigonal pyramidal shape with a bond angle of approximately 107 degrees. The NH bonds are polar due to nitrogen's higher electronegativity, and the molecule is polar overall. When answering bonding questions, always link bonding, structure, and properties. For example, explain that giant ionic lattices have strong electrostatic attractions requiring large amounts of energy to overcome, leading to high melting points. In this chapter, we've explored ionic, covalent, and metallic bonding, molecular shapes, electronegativity, and intermolecular forces. Understanding how bonding influences structure allows us to explain the physical and chemical properties of a wide range of substances.